Let's persist with the E row chart to identify metals that again satisfy now a new criterion, an E by rho greater than 0.02 gigapascal by kilogram per meter cubed, right? And the E should be greater than 100 gigapascals. E greater than 100 gigapascals would make it right here, okay? And so we are looking for options above this line over here. Now look at what the E by rho criterion is. Since it's 0.02 gigapascal by kilogram per meter cubed, this is megagram per meter cubed. So if you go to 0.1 megagram per meter cubed, that's the same as 200 kilogram per meter cubed, or sorry, 100 kilogram per meter cubed. So if you go to a point over here, that a line parallel to this line over here passes through 2 for the modulus, 2 gigapascals, and passes through 100 kilogram per meter cubed on the for the abscissa. So this is this particular line with the slope, right, parallel to this line and passing through this point satisfies the required criterion. E criterion is satisfied by materials above this line, horizontal line. The second constraint is satisfied by materials above here. So you're looking at materials in this category over here. So if you see, there are some things very close in terms of steel in this category. You might have some nickel alloys that might satisfy this criterion as well for metals. Right? Now let us see, titanium also just barely scrapes through with these combination of choices. As a fifth variant, let's continue to work with the modulus density chart and look for these two constraints. One is a horizontal line above 100 gigapascals, and the second is a line of this nature. If you look at Appendix C, what types of situations involve this material index over here? And again, we're looking for something that's 0.003 for these funky units. If you look at Appendix C, typically plates and panels, in designing those types of geometries, you come across this material index for a lightweight material. Let us go to look at how these slopes are generated. Of course, in EduPack, you will be able to enter the slope that you need. Now, in this particular case, this is a material index of choice, right? E to the power 1 by 3 divided by rho. If you take logarithms on both sides after cubing them, right, and you rearrange them, so you take a cube, m cubed is E divided by rho cubed, and then you take the denominator down over here, you will have E given by rho cubed times m cubed. If you take logs on both sides, then log E is 3 times log rho plus 3 times log m, where m is the material index. So basically in the log E versus log rho plot, you have something that you're looking for, a line of slope 3. Okay. For convenience, in this chart, you have a number of these lines, right? Similar to this previous problem, you have one more for plates and panels. You have a line over here. So E above 100 gigapascals, and then you take one of these lines and move them all the way up to this point over here when they intersect with E of 100, and you're looking at things on this side over here. If you look, you basically look at carbon fiber reinforced plastics as one of the options. B4C is another option. So if you're looking at large panels, carbon fiber reinforced plastics will come in handy. If you're looking for armor, for instance, so plates, um, boron carbide is a very good option for lightweight, high stiffness armor. So you have an epoxy and you want a specific stiffness. So E by rho that is greater than woods of different kinds. So this is your E versus rho plot. And then last week we also saw there is a specific modulus versus specific strength plot in addition. So E by rho is given by this line over here, okay, and you move it all the way to an epoxy roughly in this range somewhere, and you'll see that woods that are have a in the parallel to the grain structure, they have a modulus, so a stiffness higher noticeably than an epoxy. For those woods that are perpendicular to the grain, the direction perpendicular to the grain structure, if that's the loading, you'll see it's roughly similar to the epoxy, so it's definitely not higher in modulus or stiffer than an epoxy. Okay, so these are some things to look at as ways to work with this plot. We've gone through many combinations of just the modulus versus density plot. The same can be done with other kinds of chart combinations that we looked at last week, and also what you can come up with within the EduPack software as well.